Welcome to the Explainer. Okay, let's dive right into this. Grab a coffee because today we're putting on our senior engineer hats and walking step by step through a really notorious programming challenge. If you've ever stared at a blank whiteboard during a technical assessment and felt your mind just go completely blank, this Explainer is exactly for you. We aren't just going to look at some code today. We are going to learn how to actively decode a problem. We're going to use the clues hiding right in plain sight to build a clear roadmap to the optimal solution. So let's get started. Just 38.116%. That is the actual accuracy rate for the Count Smaller Elements problem on Geeks for Geeks, which is officially rated as hard. With over 81,000 submissions, more than 6 out of 10 attempts to solve this completely fail. What does that tell us? It tells us immediately that the intuitive, easy answer is a trap. The stakes are high here, and to be in that successful 38%, we need to think differently right from the starting line. Section 1, the hard problem statement. Before we can solve anything, we absolutely have to understand the task. We're given an array called ARR, full of non-negative integers. Our goal? Return a completely new array, res, where each position tells us exactly how many elements to the right of it are strictly smaller. To picture this, if our input in Python is 5, 2, 6, 1, our result needs to be 2, 1, 1, 0. Because, to the right of 5, there are two smaller numbers, 2 and 1. Sounds pretty straightforward, right? Well, the mechanics underneath get really tricky. Just imagine parsing through that input array. For every single number you land on, you have to scan everything remaining to its right, tally up every single value that's smaller, and log that final count into our result array. Every single index needs its own specific count. Truly understanding this direct mapping is totally crucial before we even think about writing a single line of logic. Section 2. Analyzing array constraints. Okay. Here is exactly where novices just jump straight into coding, while seasoned engineers hit the brakes. Look at this massive number. The maximum size of our input array can be up to 10 to the 6th power. That is 1 million elements. Guys, this is the platform's way of literally screaming at you that performance and optimization are going to be your biggest hurdles. Furthermore, it's not just the length of the array. The individual values inside it aren't tiny digits. The elements themselves can range from 0 all the way up to 10 to the 8th power. That's 100 million. This tells us we're dealing with integers of substantial size, meaning whatever data structures we decide to use under the hood, they need to comfortably handle large values without breaking a sweat. Section 3, the brute force trap. So, you might be asking, why can't we just write a simple nested loop in Python to check every element against every other element? Well, because that is a classic O of n squared time complexity trap. If you have 1 million elements, a nested loop is going to perform roughly 1 trillion operations. The judging system will immediately slap you with a time limit exceeded error. To survive this massive scale, we mathematically require a much more efficient approach. Section 4. O of n log n complexity target. Luckily for us, we don't have to guess what that efficient approach needs to look like. The platform explicitly tells us they expect a time complexity of O of n log n and an auxiliary space complexity of O of n. This isn't just a basic requirement, it is a massive diagnostic clue. It tells us we can trade an array's worth of extra memory in exchange for lightning-fast execution. Section 5. Algorithmic topic tags. Coding platforms almost always categorize their challenges with metadata tags. These are our breadcrumbs. Here we see arrays, sorting, and data structures. When you combine those with our O of n log n target, this points to one absolutely crucial key insight. This is an inversion count problem. We essentially need to count how many pairs exist where the left side is greater than the right side. That sorting tag, it heavily hints at using an optimized approach like a modified merge sort. Basically, during the merge step, if we place an element from the right half before a left half element, we just count it, because those are exactly the smaller elements on the right. Alternatively, looking at the data structures tag, we could use a second optimized approach. We could process the array from right to left in Python and query a binary index tree to track those smaller elements. We'd update the tree as we go, maybe even using a trick called coordinate compression if those huge 10 to the 8th values cause memory issues. So why is it so incredibly important to deduce all of this before typing? Well, look at the company tags. Google, CodeNation. These top-tier companies don't just want to see if you can write code, they want to see if you can identify an inversion count problem, proactively choose between a binary index tree or a modified merge sort, and then implement it flawlessly under pressure. Section 6. Real Interview Strategy. What we've just done here is build a highly repeatable interview strategy. Step 1, read the prompt carefully. Step 2, check those massive constraints. Step 3, use the expected complexity to rule out brute force. And step 4, match your topic tags to deduce the actual algorithm. My biggest real-world interview tip for you: anytime you are asked to compare elements with elements to their right at massive scale, immediately think inversion count and default to a merge sort or a binary index tree. All right, now it is your turn to put this blueprint into action. Head over to Geeks for Geeks and try to implement that optimal O of n log n solution yourself. If you want to see the complete Python code walkthrough and exactly how that modified merge sort looks step by step, check out the link to the GitHub repo in the description. And hey, if you found this breakdown helpful, be sure to like and subscribe to the explainer. I'll leave you all with this final thought. Over 60% of people get completely overwhelmed by the brute force trap and the massive constraints of this problem. But you have the map now. You know exactly what the constraints mean, you know what the expected complexity is demanding, and you know what algorithmic tools those tags are hinting at. So, are you ready to be part of the 38.16% who actually conquer it? Get out there and start coding. I'll see you in the next explainer.